Hi, my name is Tanya Singh, and this is my lab report, The Falling Slinky. This project investigates the falling slinky, which is a surprising physics phenomenon. When a stretched slinky hanging in static equilibrium is released from the top, the bottom does not immediately fall in the real video. My main question was whether a physics model in GlowScript could reproduce that effect. My main result was that the model captures the collapse from the top downward and shows a short delay at the bottom, but does not keep the bottom perfectly stationary the way the real slinky appears to do. The purpose of this investigation is to use a physics model to explain the motion of a falling slinky and compare the prediction to the real behavior. The system is the slinky itself, which is modeled as a chain of connected masses. The surroundings are the Earth, which provides gravity, and neighboring slinky segments, which provide spring forces. Before release, the slinky is stretched and hanging in static equilibrium, meaning that the upward spring forces and downward weight are balanced for each part. The real data comes from a Slinky drop video. In the video, the top begins moving immediately after release, while the bottom appears to remain at rest briefly before the Slinky collapses downward. From the video, the initial stretch length of the Slinky is about 0.9 meters. The bottom remains nearly stationary for approximately 0.3 seconds before it begins to move, and the full collapse of the Slinky occurs over about 0.8 seconds. These values help quantify the delay and provide a reference for comparing the model's behaviors. In my GlowScript model, the slinky is approximated as a chain of discrete masses connected by springs. Each mass experiences a gravity downwards and spring forces from neighboring masses. The top mass is initially held fixed so the chain hangs in a stretched configuration, and all the masses begin at rest. After release, the program calculates the net force on each mass and uses Newton's second law over many small time steps to update the motion. This lets the model predict how the slinky collapses over time. The main physics ideas used in this lab are static equilibrium, Newton's second law, and spring forces. Before release, each part of the slinky is in equilibrium, so the upward spring forces balance the downward gravitational force. After release, though, the net force on each mass changes, and Newton's second law determines how each part moves. The spring force depends on how much each segment is stretched or compressed. My model assumes a finite number of masses in ideal springs, ignores air resistance, and treats the motion as vertical, which simplifies the real slinky. This graph shows the main model result. The red curve is the top of the slinky and the green curve is the bottom. The top begins moving downward immediately after release while the bottom changes more slowly at first. There's a small separation between the two curves early in the motion, which means the bottom does not respond instantly. However, the bottom still begins moving much sooner than it does in the real video, so the model only partially captures the observed effect. Comparing the model to the real Slinky, the real video shows the bottom remaining nearly stationary for a short time, while my model shows only a partial delay. This means the model captures the idea that the change in force is not transmitted instantly through the Slinky, but it does not reproduce that effect perfectly. Physically, the bottom does not move right away because the forces there remain close to balanced until the disturbance from the top reaches it. So the answer to my main question is no. In my model, the bottom does not stay perfectly stationary like in the real video. In this lab, my what-if question was, what if the spring constant were increased? If the slinky were stiffer, then changes in force would be transmitted more quickly from the top to the bottom. That means the collapse wave would move downwards faster and the bottom would likely begin moving sooner. This interpretation helps explain that the delay is related to how fast the slinky can communicate changes in tension through its structure. There are several reasons that the model does not perfectly match the real slinky. First, I used a discrete mass spring chain with a limited number of masses, while a real slinky is closer to a continuous system. Second, the spring and mass parameters may not match the real slinky exactly. Third, the model ignores air resistance, damping, and other real effects. Even with those limitations, the model, in conclusion, still shows the key idea that the top responds first and the bottom responds later because changes in force propagate through the slinky over time.